this. So we know that in this unit, we've been talking about exponents. It's the exponential unit. And now we're going to shift our focus from calculating things with exponents to actually graphing them. So we're going to learn how to graph something that has an exponent in it. We did not cover this type of graph when we were learning our other unit. You know, when we did the square root function, the absolute value, and the rational. This is actually a part of it, but we kind of keep it for this unit because it sort of has a trend. Everything is dealing with exponents. If you have taken any sort of chemistry class, you probably are familiar with growth and decay. So for you, this is actually going to be a lot of review. And if you haven't taken chemistry, it's okay. We're gonna start from scratch. So, and half-life we're going to talk about as well. That'll be like on Wednesday. Yeah, but I feel like people are traumatized by me saying that. All right, you guys. So the key concepts from this lesson are we can have a function that looks like this. F of x is equal to 2 to the power of x. And when you have a base that is greater than 1, then that shows you that is an exponential growth. And you can see the graph rises up. The other type of function is where you have a base that is a fraction between 0 and 1, and that represents an exponential decay. So you can see for this graph, decay means you're starting from the left and you're falling downwards. So one is a growth graph and the other is a decay graph. And the way that you know if it's growth or decay is you look at the base and you compare the numbers. So if we were to just take a couple of notes, we would write your parent function is y is equal to ab to the power of x. I'll write that a little bit neater. So y is equal to ab to the power of x is the general form of an exponential function where a cannot equal to 0 and b has to be greater than 0 and b cannot equal to 1. If b is greater than 1, the function represents exponential growth. And if b is between 0 and 1, then that is exponential decay. So we're going to start off with a really easy example. Example number 1 says, match each graph to its corresponding equation, state whether each function represents exponential growth or decay, then determine whether the graph is increasing or decreasing from left to right. So you're going to notice at the bottom of the page, you have 4 functions, A, B, C, D. Go ahead and try this. Try and figure out which equation goes with which graph. And then tell me if it's growth or decay, and then figure out if the graph is increasing or decreasing from the right. Don't look up until you're done, but I'll go ahead and write the answers so you guys can check your work. So the values are the graphs that I got were A, D, B, C. What is the strategy that I used to this? First of all, I figured out which one of the graphs was a growth or a decay. And I know if it's a growth, that means my equation, the base has to be greater than 1. So you can see equations A and B are both greater than 1. So they have to go in the left-hand side. And the graphs on the right-hand side show a decay. And equations C and D are both fractions or decimals. So they're going to have to go on the right-hand side. In order for you to know exactly which one is which, I just put in a test value. So for example, I would pick something like x is equal to 1, and then I would quickly just sub it into my equation, and that would give me an idea of where the y value is, and I would be able to select my graph appropriately. Was this, is that okay? So for example, let's say I have equation B. See how it's 3 to the power of x? If I put in a 1 for x, that means 3 to the power of 1 is 3. So I just have to find where is 1 comma 3 a point. And that one is clearly there. And so that has to be equation B. Does that make sense? Yeah. Test value. That's what I meant by that. Yeah. If there's no vertical shift, the y feature of these. Here's a really important feature of these graphs. You're going to notice that for every single one of these graphs, they have a very specific y-intercept. So right here is 0, 1. Here it's 0, 1, 0, 1, and 0, 1. So it's safe to make the assumption that if there are no transformations in this graph, like if the graph isn't shifting up or down or side to side, all of the y-intercepts will always be at 0, 1. We don't have a graphing calculator, but if we were to graph 3 times 2 to the power of x and 5 times 2 to the power of x, what you would notice is the y-intercept would change. This one would become 0, 3, and this one would become 0, 5. And in fact, you don't even need a graphing calculator. If you put in x is equal to 0 into those equations, you're going to notice that 2 to the power of 0 is just a 1, you're left with a 3, and 2 to the power of 0 is a 1, you're left with a 5. So the y-intercept will always be the same if your equations look like this. So if they don't have any number in the front or at the end, but as soon as you add a number in the front or at the end, then you've introduced some sort of transformation and the y-intercept is going to change. And when we do the second part of today's lesson, when we talk about transformations, I'll point this out a couple of times. Let's go. Oh, we're actually going to skip example number 2. And the reason I'm going to skip example number 2 is it requires, it gives you an equation and it's basically telling you to graph it, but it requires a calculator and we don't want that right now. So we're just going to go ahead and ignore that. Are we allowed to use calculators in this unit? I'm going to have to double check. I have a feeling you won't need to. But for that reason, example number 2, we can just go ahead and skip. Let's go to the bottom of this page. So bottom of this page says attributes of exponential functions of the form y is equal to a b to the power of x. So this is the most important information that we're trying to learn from this lesson. Exponential functions have horizontal asymptotes. Luckily, we all know what the word asymptotes is because we've all learned a rational function. And so whenever you have an exponential function, there is only one asymptote and it is horizontal. Just as a review, an asymptote is a line that a graph approaches but does not reach. So it's a curved line that, it's a line that a curve gets very, very close to but never touches it or crosses it. Exponential functions of the form y is equal to a to the b to the power of x have an asymptote at y is equal to 0. And if you take a look at the diagram over here, you can see there's an exponential graph drawn over there, and the asymptote is going to be drawn with a dashed line. And we would actually say horizontal asymptote at y is equal to 0. Just like we used to label it before, it's the same thing. The y-intercept of exponential functions of the form y is equal to a times b to the power of x is located at 0, a. So whatever this number is, that is where you're going to find the y-intercept. If there is no number there, then it's 0, 1. And then we're all pretty good at domain and range now. Again, for this unit, we can just write the short form, just the condition. You don't have to write the full form. So functions in the form of y is equal to a times b to the power of x will all have a domain of x includes all real values. And that's because if you take a look at the graph, there's an arrow on both the right and the left. So the graph is basically going to extend to the right and to the left forever and ever and ever. But the range is specific, and the range is related to the asymptote. So wherever the asymptote is, you just look at if the line is above or below that, and then that is your range. So in this example, your range is going to be greater than 0. Can it include 0 if it's an asymptote? Can it touch the asymptote? No. So it can't include 0. So that, I don't know why this line is so massive, but it's just like the space to write it. It's just going to be y is greater than 0. Be mindful it does not include the value because you can't touch an asymptote. Okay, so let's try example number 3 for the graph that's given to you on the right. What is the y-intercept? You can just read that off the graph. By the way, if you could not read it off the graph, you can just let x equal to 0 and put it into the equation and solve if there was an equation given. But this one you can read off the graph. It's just going to be 0, 2. We've already established there is a horizontal asymptote at y is equal to 0. The domain is going to be x includes all real values. And like I said, we can write the short form of it, just the condition. And then the range is going to be y is greater than 0. And then we're going to circle one of these. Is this a growth or a decay? It is a growth, and we know this because the graph is rising to the right. So we're just going to circle or highlight one of those. Yeah. Yeah. Sure. What did you get? For example number 4, it says state the domain and range of the function or the part of the function shown on the graph, then determine the location of the y-intercept and determine whether the function or part of the function shown on the graph has an asymptote. So we'll do examples A and B together. You guys will try C and D yourselves. For question number 1, by the way, does this show the entire exponential function or just a part of it? Yeah, you can clearly see it's like we can't see the asymptote. We can't really see the shape of it. So this is just showing like a segment of the exponential function, but that's really all we need for this. So if we're looking at just this graph, what is the domain of this graph? Yeah, it's not x includes all real values because there is no arrow there. So we can't be sure it's x includes all real values. So we're just going to write x is greater than or equal to 0. What is the range for this? It starts at 200,000 and it goes above it. So it's going to be y is greater than or equal to 200,000. What is the y-intercept? You're just going to read that off the graph. So it's going to be 0, 200,000. And can you see an asymptote on this graph? No. And is there any way for us to know where the asymptote is without an equation? Nope, not at all, because this graph could like keep extending down to like negative 5,000. We're not sure. So we're going to say for this segment, there is no asymptote. Yeah, so because this graph is showing just a part of the exponential function, we don't know anything that happens past the 0, so we don't know if there's an asymptote or not. For the next graph, does this show a proper exponential function? Yes, it has arrows on both ends, and you can kind of see where the asymptote will be because the line starts to become more horizontal. So what is the domain in this case? It's just going to be x includes all real values because the graph continues on either side forever. What's the range going to be? It's above 0. Does it touch 0? No, there's probably an asymptote there. So it's just going to be y is greater than 0. The y-intercept, we can actually just read off the graph. It's going to be 0, 6. And it's pretty clear that in this example, your asymptote is going to be right in here because that's where our line starts to level off. So it's like a pretty good guess. So I'm going to say there's a horizontal asymptote at y is equal to 0. Okay, go ahead and try questions C and D yourselves. So I'll just leave this up here for another couple of seconds and then I'll start writing the answers. Okay, so here are the graphs if you guys want to see them. Again, example C only shows a part of it, just a segment. So this is going to be x is greater than or equal to -2. Y is greater than or equal to 16. The y-intercept is right here, which is 0, 36. And there is no asymptote that we can see. This is also just a part of the graph. So the domain here, let's say this is, there's no arrow. So it's going to be between 0 and 7. And then the range is going to be between 800 and 3,200. This will be 0, 3,200. And we cannot tell if there's an asymptote in this question. So try this. State the domain, range, and asymptote of the function shown on the graph. Which of the graphs from example 4 in this graph is this graph most similar to and why? So the domain is actually going to be pretty straightforward. It's just going to be x includes all real values. The range is going to be, what do you guys think is the asymptote? Like the most logical asymptote in this question?
0.
Yeah, it seems like it's probably going to be around 0. So that's a pretty good guess. And if there is a horizontal asymptote at y is equal to 0, that means the range is going to be y is greater than 0. And then we think that there is a horizontal asymptote at y is equal to 0. If we take a look at all the examples, which example is this most similar to? Yeah, I would say it's probably closest to example C. Yeah, exactly. And then why did some of the graphs in example 4 not have horizontal asymptotes? Because like the question said, they only showed a part of the function. You don't have enough information to figure out if it is a function, sorry, if there's an asymptote or not. Okay, let me tell you what you guys are going to be doing for homework for this part. I've given you 2 practice questions, and I'm going to post the solutions for these practice questions on Brightspace. So I'll just show this to you guys before we stop the recording. Here is page A for you guys at home. Does it look like I did? No, it doesn't. It's not my style. And here is page 2. This is a step down. Thank you for the compliment. And like I said, I will post the solutions on Brightspace. By the way, you guys don't have to do problems 7 to 12 unless you wanted to take out your calculator and graph it and all that stuff.